Hi, I'm going to go over the ratio method for AQA physics, and these are sort of the questions that might come up in both AS and A2 papers, where they give you a set of values and tell you to calculate another value if the existing values are doubled or halved, etc. So I will go over 3 questions that have this kind of types of questions and try to solve them using the ratio method. First question is question 25 from the AQA physics paper, specimen paper, which is the A2 paper. So the question goes: a fixed mass of gas occupies a volume V. The temperature of the gas increases so that the RMS velocity of the gas molecules is doubled. What will the new volume be if the pressure remains constant? So it gives us a scenario, and it tells us to find the new volume if the RMS speed was doubled. So on the side, I'm going to write the first scenario. So it tells us the fixed mass, so it's going to be mass m, and it's not going to change in the second scenario or the first scenario. Has a volume of v. We're going to assume pressure is p and RMS speed is c. For the second scenario, we want to be finding the new volume, but we know pressure is constant, so pressure in scenario 2 will also be p, but the RMS speed will be 2c because it says it's doubled. And because it says fixed mass, mass is also going to be m. So we start by stating the equation, which is if I quickly go into this first page, it is the kinetic theory model, as I can read from the formula page. So that's PV equals a third NMC squared. So we rearrange for volume. So that's going to be volume equals a third NMC squared over P. So what this ratio method works by is making an equation for scenario 2 and dividing that by scenario 1. So we can map that out doing using coefficients. So x will be the coefficient of v we want over the coefficient of scenario 1. We know that's going to be, because we know the volume is v, the coefficient is going to be 1, so it's going to be x over 1. So we map it out by first writing the equation, which is for scenario 2, which is a third nm brackets 2c squared, because the RMS velocity is doubled. Divide that whole thing by p. And then we divide that by the scenario 1 equation, which is a third nmc squared over p. We can use the keep, flip, change rule to make this into one fraction. So we keep one fraction, we flip the sign into a multiply sign, and we flip the fraction. And that gives us, if we keep going to the next, that gives us x over 1 equals a third nmc brackets 2c squared times pressure over pressure a third nmc squared. So from here we can just simplify things a bit and make it look nice. And then we can now cancel out all the the similar terms. So a third cancels out top and bottom. Pressure cancels out. Number of molecule cancels out. The mass cancels out, and also the RMS speed cancels out. So what we got left over, if you look, is just 4 over 1. So x is going to equal 4. So we know the volume of the new volume will be 4v, because 4 is going to be the coefficient of v. So the answer would be D. And I've circled it there, and as you can see, I took a screenshot from the mark scheme, and the answer is D. So the next question is question 31 from AQA Physics Paper 2, Specimen Paper, which is from the AS paper. And the question goes: a cylinder conductor of length L, diameter D, and resistivity P has a resistance R. What is the resistance of another cylindrical conductor of length L, diameter D, half D, and resistivity P? So we can tell the first scenario will be what's listed in the first sentence. So length is going to be L, diameter is going to be D, resistivity is going to be P, and resistance is going to be R. But in the second scenario, it tells us everything is the same, but except diameter is halved. So we do that. But we're trying to find resistance. So length is going to be L again, diameter is going to be half D, and resistivity is going to be P. But we're trying to find resistance. So first of all, we start by setting out our resistivity formula, which is P equals RA over L. We rearrange for R, or resistance, which is going to be PL over A. and we want to somehow get diameter into that formula. So we do know that the area of the cross-sectional area of a cylindrical conductor is going to be pi r squared, but we don't have anything in terms of the radius. But we do know the radius is a half of the diameter. So we put that into the formula, and we're going to get pi times brackets half d squared. And if you square that and simplify it, you're going to get a quarter pi diameter squared. So we can use that and plug it back into our original R equals PL over A equation in step 2. And we will get resistance equals PL over a quarter pi diameter squared. So using the same rule as before, scenario 2 equation divided by scenario 1 equation. So we'll do that in step 5, and that will give us x over 1 equals PL over a quarter pi and brackets a half diameter squared, and divide that whole thing by PL over a quarter pi d squared. As you can see, the first set is the scenario 2 and the second set is scenario 1. So we simplify things a bit, and in step 7 you can see we've joined the two fractions together by using the keep, flip, change or KFC rule, by keeping one fraction, changing the sign and flipping the other fraction. And as you can see, we have the two things at the top and bottom. But as you can see, 1 over 16 can be expressed as a quarter times a quarter. So we will do that to cancel out the next quarter at the top. So as you can see, we cancelled out one of the quarters, and we've cancelled out P, we've cancelled out the length, we've cancelled out a quarter, we've cancelled out pi, and we've cancelled out diameter squared. And we've got left over 1 over a quarter, which is basically 4. So x is going to equal 4. So 4 is going to be the coefficient. So we know the resistance of this other cylindrical conductor will be 4r, or 4. The coefficient is going to be 4. So the answer would be B, and I circled it there, and as you can see the answer is B as a screenshot from the mark scheme. And this is the last question. I don't know where I got this question from. It's from a piece of physics homework I got, but it's not sort of, there's other ways of doing this question, but I'm just going to use this question as an example to use this ratio method. So the question goes, it gives us a table of two planets and their radiuses and their densities. So planet P has 800 radius, 800 kilometers, and has a density of 600 kilograms per meter cubic meters. Planet Q has 16,000 kilometers as its radius, and the density of planet Q is half of what it is in planet P. So we can express this in algebraic terms. So planet Q will have twice the radius of planet P. So we'll say the radius of planet P is r, but the radius of planet Q will be 2r, because you can see 800 times 2 is 16,000. Sorry, 8,000 times 2 is 16,000. And same with the density. We can see 3,000 is a half of 6,000 as in planet P. So that planet Q will have half the density of planet P. And it also gives us the gravitational field strength at the surface of P is 13.4 newtons per unit mass. So it wants us to find G for the surface of Q. So in scenario 1, we know the G is 13.4, the radius is r, and the density is P. In scenario 2, we also know the G is, there's a typo in there, but G isn't 13.4, G is what we're trying to find. So that would be an X. I'll try to edit that. But the radius is 2r, and the density is half P. So we set out by putting our equation. So we know F equals the gravitational constant times big M times small m, and divide that whole thing by the radius squared, or the distance between those two planets squared. We know F equals ma, or you can express that as F equals mg, weight equals mg. So you can do mg equals gravitational constant, big M, small m, divide that by r squared. The small m's cancel out, so you get left the gravitational field strength equals gravitational constant times big M, and divide that whole thing by the radius squared. So we want to get the density somehow into that equation, so we can express it using the values we have in the different scenarios. So we don't know anything about the mass of the planets, so we're going to try to replace mass. We know we also know that the density of a material is its mass divided by its volume. So we can also express the mass to be its density times volume, but we don't know the volume. So we need to find a way how to get R into there. So we know that volume equals 4/3 pi r cubed. So we can also put that into the equation, and then we put that back into our gravitational field strength equation, and we get gravitational constant times density times 4/3 pi r cubed. Divide that whole thing by r squared. The r cubed and the r squared cancel out the powers, so you just have G equals gravitational constants times P 4/3 pi r. And as with the last two questions, scenario 2 equation over scenario 1 equation will give us the answer. But this time at the denominator of our left hand side, we don't have 1, but we have 13.4. So we have x over 13.4 equals a half GP 4/3 pi 2r, which is from our second scenario, because radius is 2r, so we put it into the equation we have at step 5. And we also know that the density is half, so we also put half there, so you can see from the numerator, and divide that whole thing by scenario 1, which is just the standard RP values. And we simplify that. So the gravitational constant cancels out, the density cancels out, 4/3 pi cancel out, and the radius cancels out. So what we have left is x over 13.4 equals a half times 2. Divide that whole thing by 1. And a half times 2 is 1. 1 over 1 is 1. But we want to find x. So we times both sides by 13.4 to get rid of the 13.4 on the left hand side. So we'll have 13.4 times 1, which is just 13.4. So the gravitational field strength at the surface of Q will be 13.4. And I got the answer, as you can see, with my shoddy working out. And I thought the answer was wrong, but it was somehow right. Well, hopefully it's right. We'll know when the homework gets marked. But it's B. And I got the same answer there, as you can see. And yeah, that's about it. If you need any past papers or resources, it's available on my site, www.umutech.net. And thank you for watching this video. Have a great day.